Air temperature data are basic to any description of weather and climate. Temperatures can be obtained in several ways. Observers can periodically read a thermometer and record the temperature. Other methods involve using thermographs or electrical thermometers that are part of automated observing stations. One basic temperature statistic that is computed each day is the daily mean. The standard procedure for determining the daily mean temperature is to average the maximum and minimum temperatures for the day. The highest and lowest temperatures that occur each day are of considerable importance and can be obtained by using specially designed liquid in glass thermometers. Mercury is the liquid used in the maximum thermometer, which has a narrowed passage called a constriction in the bore of the glass tube just above the bulb. As the temperature rises, the mercury expands and is forced through the constriction. When the temperature falls, the constriction prevents a return of the mercury to the bulb. As a result, the top of the mercury column remains at the highest point. A minimum thermometer contains a liquid of low density, such as alcohol. Within the alcohol and resting at the top of the column is a small dumbbell-shaped index. As the air temperature drops, the alcohol column shortens and the index is pulled toward the bulb by the effect of surface tension with the meniscus. When the temperature subsequently rises, the alcohol flows past the index, leaving it at the lowest temperature reached. To return the index to the top of the alcohol column, the thermometer is tilted. Another basic temperature statistic is the daily temperature range. It is determined by subtracting the daily minimum temperature from the daily maximum. On May 20th, the daily range was 24 degrees Fahrenheit. Calculate the daily mean temperature and the daily temperature range using the data from these thermometers. Fill in the blanks with the correct numbers. The monthly mean temperature is calculated by adding together the daily means for each day of the month and dividing by the number of days in the month. The annual mean temperature is an average of the 12 monthly means. That is, we add the 12 monthly means and divide by 12. Annual temperature range is computed by finding the difference between the warmest and coldest monthly mean temperatures. Mean temperatures are especially useful for making daily, monthly, or annual comparisons. Temperature ranges are useful statistics because they give an indication of extremes, an important part of understanding weather and climate. To examine the distribution of air temperatures over a large area, isotherms are commonly used. An isotherm is a line that connects points of equal temperature. Generally, isotherms represent 5-degree or 10-degree temperature differences, but any interval may be chosen. Notice that most isotherms do not pass directly through the observing stations because the station readings do not coincide with the values of the isotherms. It is usually necessary to draw in isotherms by estimating the proper position between stations. Maps with isotherms are useful tools because they clearly make temperature distribution visible at a glance. Color is often added to enhance readability. Isotherms make it easier to see areas where temperatures change rapidly or gradually. The amount of temperature change over a given distance is called the temperature gradient. Select the correct answer. Where is the temperature gradient greatest? What is the annual temperature range for Vancouver, British Columbia? Which figure best represents the temperature at point A? Which figure best represents the temperature at point B? As you examined temperature data in this section, you may have noticed that two different temperature scales were used, Fahrenheit and Celsius. The Celsius scale is in common use throughout the world, with one major exception. In the United States, the most familiar temperature scale to most people is the Fahrenheit scale. Because the interval between the melting point of ice and the boiling point of water is 100 degrees on the Celsius scale and 180 degrees on the Fahrenheit scale, a Celsius degree is larger than a Fahrenheit degree by a factor of 180 over 100, or 1.8. So, to convert from one system to the other, allowance must be made for the difference in the size of degrees. The formulas must also adjust for the different 0-degree points with the plus or minus 32 factor. In this sample problem, we first subtract 32 from 50 to get 18. Then we divide 18 by 1.8 to get 10 degrees Celsius. In this sample problem, we first multiply 1.8 by 20 to get 36. Then we add 36 and 32 to get 68 degrees Fahrenheit. Select the correct formula and then convert 35 degrees Celsius to Fahrenheit. Fill in the blank with the correct answer. Select the correct formula and then convert 41 degrees Fahrenheit to Celsius. Fill in the blank with the correct answer. The term greenhouse effect is used to describe the process by which the atmosphere is heated. We know that about 50% of incoming solar radiation passes through the atmosphere and is absorbed at Earth's surface. Because Earth's surface is much cooler than the Sun, it emits longer wavelength radiation. Much of the longer wavelength radiation from Earth is absorbed by certain gases in the atmosphere. The primary heat-absorbing gases in the atmosphere are carbon dioxide and water vapor. After water vapor and carbon dioxide absorb outgoing Earth radiation, they re-radiate this energy away in all directions. Some travel skyward where it may be reabsorbed by the atmosphere. Some of the energy travels earthward and is absorbed by other gas molecules and by Earth's surface. In this manner, the atmosphere is heated because it traps a portion of the outgoing Earth radiation. Without absorptive gases in our atmosphere, our planet would experience an average surface temperature far below freezing, and Earth would not provide a suitable habitat for humans and other life forms. This very important process is called the greenhouse effect because it was once thought that greenhouses were heated in a similar manner. In summary, the greenhouse effect works this way. Because gases are selective absorbers, the atmosphere transmits most incoming solar radiation to Earth's surface where it is absorbed. Air is heated when water vapor and carbon dioxide absorb the longer wavelength radiation emitted by Earth. The greenhouse effect is related to a significant and very complex global environmental issue, global warming. Because carbon dioxide is an important heat-absorbing gas, any change in the air's carbon dioxide content could alter temperatures in the lower atmosphere. The proportion of carbon dioxide in the atmosphere has been rising steadily for more than 200 years. Human activities, especially the combustion of fossil fuels, have led to a carbon dioxide increase of more than 30% since 1750, and it keeps growing. The concern is that global temperatures are increasing significantly due to an enhanced greenhouse effect. Given the increase in the atmosphere's carbon dioxide content, are global temperatures already on the rise? The answer is yes. The statements above are based on a report by the Intergovernmental Panel on Climate Change. The bar graph clearly indicates that there are significant temperature variations from year to year, but the graph also shows a trend. Estimated global mean temperatures have been above the 1961 to 1990 average every year since 1978. Globally, the 1990s was the warmest decade. 1998, 2005, 2002, 2003, 2001, and 2004 were the warmest years since 1861. The effects of a significant temperature increase are of great concern and much uncertainty. Many impacts are possible, including a shift in storm patterns and a rise in sea level. What paths does solar radiation take once it is intercepted by Earth? Scattering is the process by which gases and tiny particles in the atmosphere redirect solar energy. Scattering explains how light reaches into a shaded area or a room when direct sunlight is absent. Some solar energy is reflected back to space. It leaves in the same short wavelengths in which it came to Earth. On the average, about 30% of the solar energy intercepted by Earth is reflected and scattered back to space. The percentage of the total radiation that is reflected by a surface is called its albedo. One type of image generated by weather satellites is a visible image. Such images actually measure albedo because they measure the intensity of visible light reflected by clouds and by Earth's land and sea surface. The albedo of land and water surfaces is generally low. By contrast, a cloud's albedo is generally high. It's easy to distinguish the clouds from Earth's surface in this image. The percentage of light reflected from clouds varies. Thick clouds have higher albedos and are bright in the satellite image. By contrast, thin clouds have much lower albedos because they are semi-transparent to sunlight. Some solar energy is absorbed directly by the atmosphere and clouds. As you can see, the percentage is relatively small. By far, the largest percentage of incoming solar energy passes through the atmosphere and is absorbed at Earth's surface. Thus, the atmosphere does not acquire the bulk of its energy directly from the sun. As we will see, it is heated mainly by energy that was first absorbed by Earth's surface and then emitted by the surface to the sky. The percentages shown here are global averages. The actual amounts can vary because several factors can cause albedo to vary. If the percentage of light reflected back to space varies, so will the amount taking each of the other paths. Select the best answer. If the amount of cloud cover were to increase, how do you think albedo would be affected? Try ranking these various surfaces from highest to lowest in terms of albedo. The angle of the sun's rays influences the percentage of light reflected. The lower the sun angle, the longer the path through the atmosphere. A longer path through the atmosphere increases the amount of scattering and reflection. When albedo increases, there is less solar energy available to heat Earth and its atmosphere. When albedo decreases, more energy is available. Most of us realize that the sun is the source of energy to heat Earth's surface. But how is this energy delivered from the sun to Earth? Solar energy makes its way to Earth by an energy transfer mechanism termed radiation. The sun emits light and heat as well as the ultraviolet rays that cause suntan. Light, heat, and ultraviolet light are only a part of a large array of energy called electromagnetic radiation, or simply radiation. In some ways, the transmission of electromagnetic radiation is similar to ocean waves. Like ocean waves, electromagnetic waves come in various sizes. The electromagnetic spectrum is divided on the basis of wavelength. Gamma rays have the shortest wavelengths, less than 1/billionth of a centimeter. And radio waves are longest, with wavelengths that can be kilometers long. Visible light, as the name implies, is the only part of the spectrum that we can see. Visible light actually consists of a mixture of colors, each corresponding to a different wavelength. This can be demonstrated by passing sunlight through a prism. Each wavelength of light is bent differently, producing a familiar array of colors we call the colors of the rainbow. Violet has the shortest wavelength and red has the longest. Located next to red and having a longer wavelength is infrared radiation. Infrared radiation is not visible, but we feel it as heat. The closest invisible wavelengths to violet are called ultraviolet and are the rays responsible for causing sunburn. The ultraviolet index is a forecast of the amount of skin-damaging ultraviolet radiation expected to reach Earth's surface at the time when the sun is highest in the sky. The amount of UV radiation reaching the surface is primarily related to the sun angle, the amount of ozone in the stratosphere, and the amount of cloud cover. The UV index ranges from 0 to 11 or higher. The higher the UV index, the greater the dose of skin-damaging UV radiation. Consequently, the higher the UV index, the shorter the time it takes before skin damage occurs. How much UV radiation is needed to actually damage one's skin depends on several factors. In general, the darker one's skin, the longer it takes to cause skin reddening. Drag the correct label to the appropriate spot on the electromagnetic spectrum. Drag the color to its correct position on the spectrum for visible light. Although electromagnetic radiation is divided into categories, all forms are basically the same. When any form of radiation is absorbed by an object, the result is an increase in temperature. To understand how the atmosphere is heated, it is helpful to learn some basic laws governing radiation. One basic law governing radiation states that all objects, at whatever temperature, emit radiant energy. A second basic law states that the hotter the radiating body, the shorter the wavelengths of maximum emission. When the hot metal first leaves the fire, it glows white-hot. As its temperature cools, the color changes because the wavelengths emitted get longer. One type of image generated by weather satellites is called an infrared image. An instrument on board the satellite detects various infrared wavelengths emitted by Earth's surface and atmosphere. Infrared images provide a way of determining which clouds are the most probable precipitation producers. The high tops of towering storm clouds are colder than the tops of clouds that are not as tall. In this image, the highest cloud tops are associated with towering storm clouds that are part of Hurricane Isidore in the Gulf of Mexico. The tallest clouds, and thus the heaviest rain, are in the areas shaded red and yellow. Because the surface of the Sun is so much hotter than Earth's surface, the Sun radiates maximum energy in the shorter, visible range, whereas the much cooler Earth radiates maximum energy in the longer, infrared range. Another basic law related to radiation states that objects that are good absorbers of radiation, such as Earth's surface, are also good emitters. By contrast, gases are selective absorbers and radiators. Thus, the gases composing the atmosphere are good absorbers and emitters of some wavelengths, but do not absorb or emit other wavelengths. Experience tells us that the atmosphere is transparent to visible light because it readily reaches Earth's surface. By contrast, the gases composing our atmosphere are capable of absorbing and emitting much of the longer radiation emitted by Earth. Let's recap some important points regarding radiation.